My name is Andrea Copping, and I am with Pacific Northwest National Laboratory in the US. I also have a faculty appointment at the University of Washington in Seattle, Washington. And the information I'm going to provide for you today really comes from quite a large team of researchers, but I particularly want to note my colleagues who helped to lead this program with me. Rob Cabanero at Pacific Northwest National Laboratory, also Scott Jenny and Seno Sirnavas at the National Renewable Energy Lab. And happily, Senu has already set the stage for me and talked a little bit about the US Department of Energy National Laboratory, so I don't need to do that. What I'm going to talk about today is the initiative called Powering the Blue Economy, a specific part of it, where we are using marine energy to try to support ocean observations. This is a US Department of Energy initiative, but the two laboratories, Pacific Northwest National Lab and the National Renewable Energy Lab, are in the position of leading it. So just to, oh boy, now there we go. Just to set the stage a little for Pacific Northwest National Lab, so you know where we are. Here we are in the US, of course, and we are the only national lab that has a marine station. Very fortunate in that. And if you look at the map of the US, we're way up here in the northwest corner in the state of Washington. And our laboratory, this is the state of Washington over on the right. You see the, oops, come on back, the little stars. Our main campus is over in the desert in eastern Washington, but our marine lab is up on the Pacific coast up here in a town called Sequim. And when you get into Sequim, into the shoreline here, this is an aerial view of our marine laboratory. What you see is a collection of buildings and a pier right down on the water, and we have the ability to, oh dear, I keep going forward by mistake, sorry. We have the ability to deploy from that dock. We have a small cabled array we're just installing in this area. It's quite a swift tidal current, not swift enough to generate power, but it is quite representative of small areas. And we have flowing seawater and all the great things you have in a marine lab. The other set of buildings you see are actually several hundred, a couple hundred meters up in the air from the lower, what we call the beach installation, and that includes a whole set of analytical chemistry labs, test facilities, etc. So that's where we are. So, Powering the Blue Economy. This is an initiative that the Department of Energy has undertaken with marine energy, particularly wave and tidal energy, with the idea that these are not yet cost competitive technologies with, say, offshore wind or solar, but there are perhaps many niche markets where this would be appropriate. And through this initiative, we are attempting to assess the value that marine energy might bring to these emerging blue economy end uses, which include powering remote communities, islands, and so on. And we are attempting to develop and deploy marine energy devices based very much on the end user need. So we know whatever we're producing will have an end use or a market. And through this, we hope to accelerate marine energy technology readiness, both at the small blue economy scale, but also for the grid scale. About 2 years ago, staff from Pacific Northwest National Laboratory and the National Renewable Energy Lab produced this report you see the cover of over on the right. There's the link. This is where we assessed a whole range of, we called them markets, they're really end uses for the blue economy. And we divided those into two groups. One group we called Power at Sea. That is generating power for use out in the ocean. And those include things like ocean observations, recharging underwater vehicles, aquaculture, and so on. And the other group we called Resilient Coastal Communities. And this is providing power to islands and isolated communities, also being able to desalinate water and provide for disaster recovery. And the graphic you see over on the right just indicates this, that the resilient coastal community uses, like power to islands, etc., tend to be within about 2 nautical miles of the coast, and there will be an export cable for taking power ashore. The power at sea markets over on the right tend to be further offshore, and in most cases there will be no cable. It will be producing power for use in situ. And this is the ones here are what I really want to talk about today. So what we have done between the two labs is develop a research and development program that's been driven by end users and applying an engineering design approach. We started by identifying those uses where we thought the powering the blue economy, the small marine devices might make sense. We have had an extensive outreach program where we've engaged with end users to understand their needs. We've then developed a series of use cases and applied an engineering lens to look at the functional requirements that would be needed to achieve those use cases. And we're now moving towards research and development projects that will really look at how you can reduce the constraints and barriers, understand how we might apply these marine energy devices, specific marine energy devices to specific end uses. And through this, we have developed, 10, let me just talk a little bit about the end user discovery. In order to do this for ocean observations, we've interviewed more than 50 ocean obs experts, and we asked them a whole series of questions. And that included things like, what domain do you work in? Do you work on the surface, the subsurface, the shelf, deep ocean, etc.? We asked them how much power their devices required. And then we also posed the question, what if we could provide more power to you? What future uses would you need would you put that power towards? We also asked them, if we were to provide additional power that allowed you to leave your devices, your platforms, your vehicles out longer, what are the next constraints that would come up? And that would include things like biofouling and drift of calibrated instruments, etc. And what you see on the right, on the top, is the outcome where we asked about how much power they required for their devices. On the y-axis, you see the different kinds of ocean observation platforms, vehicles, sensors, etc. And on the x-axis is the amount of power needed. And you'll note that is in watts, not in kilowatts or megawatts. And what you see is the vast majority of ocean observation devices use 10 watts or less. The exceptions are things like recharging autonomous underwater vehicles, perhaps having a high frequency radar, etc. So this is sort of some of the targets we can look at. In the lower left graph, you see the same thing. If we parse these power needs by domain, from the surface, subsurface, that cut off a little, you'll see the blue bars indicate that watts are needed most commonly for most of these applications. On the lower right, this is just a series of the comments we got back on what would you do with more power. And the first ones include having longer deployments for devices, higher sampling rates, and being able to add more sensors and more options on how data are collected. And also improved communication, the ability to telemetry data more effectively through satellite or cell systems. And then there's a whole series of other things that people would like more power for. It was interesting as we talked to these people, their initial reaction is, we don't need more power. We've worked for decades to make these devices use very little power. But once we sort of provided that vision of what if you had much more power, what would you do? There was a lot of excitement and a lot of interest in engaging in these processes. So with this information, we added together with several other sort of opportunities that we saw. Part of that was partnership opportunities. Government agencies, universities, and private firms interested in partnering with us in these processes. We looked at the literature, of course, to see what has been done and what seems feasible. And we looked at a number of these high risk, high reward kinds of potential activities, and looked to where, of course, the US Department of Energy has money. And from this, we developed 10 ocean observation use cases. A series of them, 6 of them, really address common needs and challenges, something we have to face if we are to provide marine energy to any of these offshore applications. The other 4 were more specific sort of locations or end uses. And what I want to do with the rest of my time here is really talk through these use cases and give you a flavor of the kind of work we have been engaged in. Whoa. So the very first one is efficient power systems. We know that marine energy sources are periodic when you think of waves or tides. That is very different than other types of energy generation. You often get really high peak to average values, and this is not necessarily easy on many types of standard power takeoffs and electrical systems. So we are working to design power systems that are capable of really handling this periodicity and benefiting from it. We have 2 projects that have been ongoing, modeling and eventually to go to bench scale testing, one for tidal and one for wave, because they differ considerably. And each lab is addressing one of those. The second use case, we are characterizing the interference that might come from a marine energy device providing power to an ocean observation platform. For example, if you were to power a wave measurement device, buoy at sea with a wave energy converter, you have to ensure that the motion from the wave energy converter does not contaminate the wave measurement signals. Alternately, if you are trying to power a series of hydrophones on a fixed platform to listen to, say, for marine mammals, as is pictured here. And if you're using a tidal turbine, you want to ensure that the acoustic output from that tidal turbine does not interfere with that, with the acoustics you're trying to acquire from the marine mammals. So we're trying to look at both motion and acoustic interference, which is possibly going to affect many of these kinds of uses. We've had to look at the reliability of these marine energy systems because effectively we would like to replace some of the current systems. Most ocean observation platforms, both fixed and mobile, run on battery power. There is some augmentation for surface buoys with solar panels, sometimes small wind turbines. So if the marine energy devices aren't at least as reliable as these, there would be no purpose to using them. To do this, we looked at a series of meteorological buoys and looked at their failure modes, and particularly when they stopped transmitting data, etc. What we found, though, was that generally speaking, the power is not really what is the greatest failure mode. I'll talk a little bit about that later, but we did a number of analyses along those lines. Led by the group at the National Renewable Energy Lab, there has been an extensive modeling effort to look at small wave energy converters, recognizing that most of the work that's been done in the past has been done for larger scale devices with larger waves, trying to really maximize the power output. But instead, NREL scientists looked at several archetypes like the oscillating surge, a point absorber, and an attenuator at a small scale with small waves to understand what kinds of outputs we might need in these sort of 0 to 10 or 100 watt range for ocean observations. And they have produced a large publicly available interactive data set that can be downloaded and used by anyone trying to work in this realm. Also led by NREL, we have been looking at the possibility of using desalination from wave power. Wave power can be used directly, the mechanical energy from wave power to desalinate seawater. There's no need to go through electricity to get there. This won't work for very large desalination efforts. Most of those are connected, of course, on land to large electrical plants, etc. But for things such as emergency response, isolated communities, this is a real possibility where modular systems could be shipped and put into operation. But in order to really understand this, it's necessary to know what those uses are. Those end uses would be, what the requirements would be. And so this has been a journey of customer discovery, really understanding what might be needed here. So the next use case we've looked at is mooringless station keeping. I mentioned that the reliability of these moored systems does not seem to be reliant so much on power, but rather it is the moorings that are the most common failure point. So we have investigated whether it is possible for marine energy to act in a mooringless station keeping manner. That is, having some kind of propulsion or other means to stay on station or within a small watch circle, but not include a mooring. And we've done sort of a deep dive into the literature on things like dynamic positioning. And then you see over on the right there, the sail drone. If you're not familiar with this, you should look it up. This is an autonomous vehicle that is powered by wind and a little bit of solar and is able to receive commands and carry out missions without the presence of either a mooring or any kind of operator. And we are still examining this because while wind and solar seem to be obvious here, we do believe that there is some possibility of creating these devices, particularly for places like the center of the ocean gyres, where we're looking at climate change solutions and so on in ocean observation. So that one's still sort of a work in progress. So those are all the use cases that kind of go across the challenges and barriers. We have also created 4 use cases for more place-based, very specified ocean observation capabilities. And the first is in the Arctic. We have the US and many other countries have buoys both in open water, on the ice edge, and on the ice to look at changes in Arctic ice, in currents, in water temperature. This is a very key piece of climate change research worldwide. Yet when you put these devices up here, it's very difficult to ever maintain them or change the batteries. So generally they last a winter and then they are destroyed. What if we could generate power in situ for these uses? And we've looked at a number of potential applications here, including the very small current that is generated as an ice flow goes across the surface water. Looking at turbines for that, for vortex-induced vibration, etc. We're also interested in how do we get power to the deep ocean. There are cabled arrays, of course, for ocean observations in a number of parts of the world, but there's also many autonomous stations and vehicles that are run on battery power. So we have examined it sort of from the top and the bottom. How would you get power generated by waves at the surface to depth, probably not deep depths, but perhaps 100 meters? And also, if you're trying to work in the very deep ocean, in the 5,000 meter plus depths, is there a possibility of generating power from the hydrothermal vents? We know that there's a huge amount of heat and power, et cetera, coming out of these vents, and that's what you're seeing in this. The dots on this map here are the known hydrothermal vents. This is still a work in progress because, as you can imagine, these atmospheres around the hydrothermal vents, very, very superheated water full of a lot of very, very corrosive chemicals. But we're continuing to examine that possibility. The next use case we've been examining is looking at ocean gradients. In terms of thermal gradients in the ocean, the Argo floats, of course, are used worldwide to profile from up and down through the water column to usually about 2,000 meters depth, though some go deeper. They use a buoyancy engine based on generally phase-changing materials from the thermal gradients they pass through. Our team has been looking at the use of newer materials that may be more effective, more efficient, and also at improving the efficiency of the buoyancy engine itself. We've also been looking at salinity gradients in the ocean as a potential for generating power. We've come to the conclusion that the open ocean salinity gradients are simply too small to generate sufficient power to be practical, but we are examining the larger salinity gradients at the coast where fresh water may enter seawater and therefore be more, have a greater gradient. And our last use case over the past year or so has been around large animal telemetry tags. As climate change and humans encroach more and more on the animals in the ocean, we have a greater and greater need to understand what these animals are doing, what their normal behavior is. And we do this with the use of tags. This drawing here is the kind of tag that's generally put on a whale. It's a temporary tag put into their skin, and it falls off and the battery dies. They also put little backpacks on sea turtles, glue things to the heads of seals, etc. And power for these, again, is very limited because the battery size is small. So we are examining the possibility of using the animal's motion itself, the inertia, to perhaps recharge these tags. It doesn't need to be a great deal of power again. So that's sort of the journey we've been taking through these use cases. And where we are right now is we are moving forward over the next 2 years with a subset of these use cases through a design, build, test process. Where we are building at the designing and building at the bench scale. And then eventually with many of these, we hope to test them in the field right off our dock at the swim lab I showed you earlier on, the Pacific Northwest National Marine Lab. The ones that we're going forward with is the efficient power systems. That's creating power systems that will deal well with the periodicity of both wave and tidal. The tidal work is being done at Pacific Northwest National Lab, and the National Renewable Energy Lab researchers are looking at the wave side of that. We have just, for the Arctic, we have just purchased a small device for vortex-induced vibration so that there's just that small amount of movement that generates power. And we believe this is going to be sufficient for some small sensors that are mounted on the ice, if we can, and we're working to how you would make that connection with the power. We are continuing to work on the efficiency of these thermal gradients, these buoyancy engines for floating, profiling floats through the thermal gradients of the deep ocean, and have had some really interesting advances with some of the materials we're looking at. We are also looking at salinity gradients for coastal sensors. We have a lab, a bench scale operation of understanding how much power can really be generated from these salinity gradients at that sort of small scale for powering sensors in coastal areas. Now, in most areas, you'd have grid connected power, and there'd be no reason to go for marine power. But we do have in the US, and I think in most countries, in very isolated areas, a need for better understanding of everything from high frequency radar for weather prediction, search and rescue, and so on. And in many cases, what is slowing these kinds of deployment of sensors is the lack of power. And we do have 2 field programs planned for both looking at acoustic and motion interference from marine energy powering sensors. We'll be looking at a listening system for the endangered southern resident killer whale, or orca, in my backyard in Puget Sound, for powering with a tidal turbine and looking at the potential acoustic interference, and doing the same thing with wave motion interference for powering wave buoys, powering wave measurement buoys. Interestingly, the motion sensing or motion damping and motion interference capabilities we are adopting largely from the film industry. As Hollywood tries to make movies at sea where there's any kind of real rocking motion, there's a need to damp this, and they've solved several of those problems for us already. And then the final project that the 2 labs are putting forward right now, we're just still in the planning stages for, is the 3D printing of a tidal turbine, starting with tidal blades, but then eventually being able to print an entire cross-flow turbine to really relieve the need for many of the bolted together components that tend to be the failure locations. And finally, we're working with a series of university students. We have 2 projects going on right now. One, the students have been challenged to design and build a small version of a through ice tidal turbine. So this would be for powering small ice-mounted sensors in the Arctic. This would require a turbine that would be able to drill itself through the ice, attach to the bottom of the ice, and send power to the surface of that ice flow. We're not sure we're going to actually get to test that one in real time, although we do have an Arctic lab at our field station that allows us to produce sea ice. And the second group of students are working on this efficiency of the mechanical to electrical power in the small thermal buoyancy engines. There's a number of different components here. We have a bench scale operating thermal buoyancy engine, and the students will be helping to interface to really try to see where those last little bits of efficiency can be derived. And that's the program we're taking a part in right now. My email is there, and that is the connection, the URL where there's a great deal more information on powering the blue economy. And one of the reasons that I wanted to talk about this here today is I think this is a problem or an opportunity worldwide. Every maritime country has some hand in ocean observations. It's a very big worldwide community, and we're all facing exactly the same problems of not having enough power. So among other things, I'm hoping that there might be people listening with an interest in ocean observations and an interest in collaboration. So thank you very much. I look forward to any questions.
Thank you, Andrea. That was a fascinating presentation and a fascinating research program, I need to say. And I totally agree that observation is a key for a better understanding of the oceans and of the interaction between the offshore renewable energies and the physical parameter and ecosystems. So I'm looking for the question. There is nothing specific coming up yet, but I do have a couple of one, if I may.
Mm-hmm.
I really like the idea of the mooring life station keeping sensors, and I have some experience with, for instance, wave buoys. And you mentioned that the issue was that the mooring line could break. So in my experience, there is two sources of breakage. Fishermen that by accident or not cut the lines, and storms events. And I was wondering whether you run tests in extreme events with this kind of autonomous sensors.
We haven't had very much experience ourselves, but the sail drone here, this is really kind of a neat story. This sail drone here, this is a private company, but the National Oceanic and Atmospheric Administration, which is the government agency in the US that really is involved most in ocean observations, they have used a series of these sail drones, and they circumnavigated Antarctica a year and a half ago and collected data the whole way. And these devices survived very well. We have other experience, and we have a little more hands-on experience on something called a wave glider, which looks like a surfboard with sort of window blinds underneath it where it moves with the waves. And we've had good luck with that, and it hasn't been tested in as extreme conditions as the sail drone, but it has been, boy, I can't get out of my slides now. How funny. But so we have had some experience here. Trying to stop my slideshow and I can't seem to. There we go.
Okay. Thanks
so, yes,
a lot.
I think some of these have real possibilities. The other thing is we looked considerably at dynamic positioning, which is of course what's used with the big floating oil rigs and big ships. But those of course are enormous, take a lot of power, and are very expensive. So we're really interested in some of these more less expensive solutions, smaller solutions, but also ones that can be manufactured quite inexpensively and eventually to be incorporated into whatever the ocean observation platform is. I think that's the real key, is to have an integrated system.
Okay, thank you. And one last question from my side, sorry. So it's not directly connected to what you presented, but I was wondering whether you are also considering data transmission issues, or maybe either within this program or the next one, because I would say that beyond autonomy, the fact that you may lose all the data if you use the sensors is a big issue for the community, as you know.
Absolutely. Power for the sensors comes first, and data transmission communications is a very important one when we talk to the end users. And we are not engaging tremendously in the communication side of it. It's not really our expertise, but providing power for communications, absolutely. And one of the things we found with the ocean observation community is it's a very large, vibrant community. We try to understand what their needs and failure modes are and address them and stay out of the communication side that they're much more expert in. But you're absolutely right. Anything that is far out at sea, depending on data acquisition that you then have to go and retrieve, is really a problem. We have to do better with data transmission, and with so many of the new inexpensive satellites going up from Starlink on, there is every reason to believe once upon a time, satellite communication from these offshore devices was really expensive, but those costs are coming down very, very quickly. And we think that if we can provide that extra power, that there's real opportunity to improve that situation.
Okay, great. Yeah, that sounds like a very promising perspective. Thank you very much, Andrea.